Alrighty, so in this video we are going to be taking a look at the ideal gas law and deriving it from scratch. What a fun idea. Alright, we're going to start with this cubic container. The cube is, we'll say, a side length L. So it has side width, length, and height L, interior dimensions. And there is a particle of mass M moving with some speed, and that speed is given by the RMS speed, the root mean squared speed, or root mean squared velocity. And let's just pick a random direction because they're all moving in random directions. So this is an average particle. We're going to take a look at the change in momentum of this one particle and how that applies a force to the wall. And then we're going to increase that force by a factor of n, the number of particles that are in the container, not just one. It's a very low density gas. And then figure out the force acting on the side of the container and the pressure, which is the force divided by area, and how those things are related to each other and how that gives us the ideal gas law. So let's see where this goes. So we currently are going to see this particle, and it is going to travel on a path that leads it to the wall, bam, and then rebound perfectly elastically is the idea. That these particles will rebound perfectly elastically. I don't know what size to do this. That one. Okay, boom. Whoa, too big. Undo. That one right there, maybe. Boom, sounds good. All right, and so what's happening then is this particle is rebounding, and it still has the same speed because the collision is perfectly elastic, VRMS. But what has changed is the x component, which we will call Vx. And so the Vx component was negative initially. It was going towards the wall to the left, and now it is going to the right, positive, and the y, and if we drew them z, which is coming out of the screen, the z components would be exactly unchanged by this collision with the wall, because the wall can only apply a normal force, and normal forces, by definition, are always perpendicular, right? The normal force, and so it can only change the perpendicular component of the velocity, which in this case is the x component. Now I'm using this term Vx here to represent the x component of the RMS velocity. So it's really V RMS comma x, but that seems like a lot to write, and so I'm just going to call it Vx, if that's okay with you. And if it's not okay with you, then stop watching, because it's my choice. It's my video. Sorry, it's late, and let me see the time clock, and then it's 9:45. I did this already once, but I didn't have my microphone turned on in my screen recording, and so it's just a 10-minute video of me just moving things around on a screen. Lovely. Anyway, what we want to do then is take a look at the momentum, the change in momentum specifically for this particle. And so what I'm going to do is pop over there and then say the change in momentum for this particle. That's a lowercase p. Capital P later is going to be pressure. The lowercase p is the mass multiplied by a change in velocity. Well, this is clearly the mass multiplied by the final velocity minus the initial velocity. Script v on that one, look at that. But we only care about the x component, right? The y and the z components are not changing, and so our change in momentum, therefore, is m multiplied by our final velocity is vx, and our initial velocity is a negative vx. Okay, and that gives us a change in momentum of 2 multiplied by m multiplied by vx, because we have a vx minus a negative vx, that's a plus vx, adding them to mvx. Hopefully that's fairly straightforward. Okay, now we don't care specifically about the change in momentum of this. We care about the force, right? That force that it applies to the wall or that the wall applies to it. They're the same magnitude because of Newton's third law. And that force, we know, this is the average force from one particle, is going to be a change in momentum divided by a time, right? This is the definition of impulse, is force times time, is the change in momentum. We know the change in momentum, we just need to know the time interval. Well, how much time does it take for a perfectly elastic collision with an atomic molecule, or a molecule colliding with a wall? Atomic molecule, listen to me. Anyway, colliding with a wall. Well, it's nigh instantaneous. That doesn't really help us much. But what I do want us to think about is how much time happens between collisions. Let's say we only had this one particle bouncing around inside this box. It's going to keep on going, boom, 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 right? It's going to keep on bouncing around and keep on going, keep on going, keep on going, bouncing off perfectly elastic collisions every single time until eventually it's going to come back and hit the wall again. Bam! So right there, it's going to hit the wall a second time. How far has it traveled? Well, it's traveled a great distance, but we only care about the x component of the velocity because the y and z components are independent, and so whatever speed is moving in the x, it's going to travel from the wall. It's going to travel, let's do yellow, okay, it's going to travel over to this side and back again before it hits, okay? And so the distance that it travels, right, that displacement is 2 times the length. And so we know that the velocity is given by a displacement over time, right? And so that gives us the idea that the time interval, the time between collisions, is the distance it travels divided by its speed, which we are calling Vx, the speed in the x direction. But this is equal to 2 times L over Vx. So that's our time interval. That's going to go right in over here for our force equation. So this is going to be 2 times m times my speed, x, the x component of my RMS velocity, divided by 2L over Vx. Well, denominator of a denominator becomes the numerator. It's kind of like the enemy of my enemy is my friend, right? So this gives us our average velocity is going to be, and our 2's cancel out nicely. Oh man, I love it when that happens. And so then we get m times Vx squared, ooh, that's going to be important later, over L. Great, that's our average force. Now, if we have n particles, then the total amount of force applied to the wall is going to be equal to n multiplied by the average force applied by one particle. And so then we get n times m times speed squared over L. And that is the force. But it's a gas. We don't care about force only. We care about pressure, right? And this is our capital P for pressure, is going to be equal to our force divided by our area. We know the force, we just got that. What's the area of one side of this cube? What's the area over here? Well, this area over there is going to be L squared, isn't it? That's the area of that wall over there. And so that force is going to be divided by L squared, which hopefully we can see is n times m times the speed in the x direction squared, divided by L multiplied by L squared. Well, L, the length, times the area, length times area, is the volume. And so we get this idea that the pressure is equal to n times m times speed in the x direction squared divided by the volume. This is not a speed, this is a capital V volume. I know we've got lowercase p's, we've got capital P's, we've got lowercase v's, we've got capital V's. It is just a nightmare, okay? But we're keeping track. We're doing fine. And what this gives us now at this point is P times V, both capital, is equal to n times m times a lowercase vx squared. Okay, well that is not the ideal gas law. That is not. I don't know if you know the ideal gas law. We're getting there, but that is not it. What do we do then? Well, we go back to the relationship that we have between temperature, which is in the ideal gas law, and speed, which is in that Vx squared right there. So that relationship, if we recall from our definition of our RMS speed, remember that speed we had at the very beginning, is the square root of 3 multiplied by Boltzmann's constant, Kb, divided by the mass, T in the numerator also, which would tell us that the square of our RMS speed, if I square both sides, is 3 times Boltzmann constant multiplied by temperature divided by mass, or if I divide by 3 on both sides, why I'm doing this will be very clear in a minute, is equal to Boltzmann constant times temperature over mass. Now, why did I do that 1/3? Well, I don't have the RMS speed. I have the x component of the RMS speed. Well, if we think about the Pythagorean theorem, or a vector of some kind, right? If I have some vector and I call it v, then the x component and the y component relate to v by saying that v squared is equal to vx squared plus vy squared. And I hope you agree with that. But it's also true in 3 dimensions. So if I had a 3-dimensional vector, it would be vx squared plus vy squared plus, you guessed it, vz squared. Zoom. Sorry about that. And so we can do that with our RMS, right? Our VRMS, the root mean squared speed, it's a 3-dimensional vector, right? The speed can be in any direction at all, any direction of space, is Vx, the x component of that RMS speed squared, plus the y component squared, plus the z component squared. But if we think about averaging these things over the trillions upon quadrillions of values, these 3, the x, y, and z, are all equal. The average z component squared is equal to the average x component squared is equal to the average y component squared, because the velocity is equally likely to be in any direction, and so they all average out to be equal to each other. And so what that means is, since we're dealing with x, what we can say is that all of them are x squared. So VRMS squared is vx squared plus a number that's exactly equal to vx squared plus another number that's exactly equal to vx squared. And hopefully you can see that that equals to 3 times vx squared. Now you know why I like that divided by 3, because I get 1/3 of my RMS squared value is equal to the x component squared. Look at that. Look at that. So then I can change color again. Change color again. What am I doing this time? Ooh, green. I haven't done green yet. Oh, that's kind of too close to the other one. Brown. We'll do brown. Okay, so I have this idea that 1/3 the RMS speed squared equals the Vx squared, but that also equals, and I go zoom back up and I get my Boltzmann constant temperature mass idea. So I then have Boltzmann constant times temperature over mass has to be equal to the x component of my RMS speed squared. That is going to go in right over here. That's where that goes. Right there. So I am then left, we'll go back to my nice dark red. I like it the most. Pressure multiplied by volume is equal to the n, the number of particles, multiplied by m, multiplied by Boltzmann constant temperature over mass. My masses cancel. It doesn't matter what gas I'm talking about. Argon, helium, doesn't matter. They cancel out. So I'm left with pressure multiplied by volume is equal to the number of particles multiplied by Boltzmann constant multiplied by the temperature. This is the ideal gas law right there. That's what it is. That's exactly it. If you wanted to deal with units of moles, if you didn't like giant numbers, then you could use units of moles and use lowercase n instead of capital N, but you'd have to use the ideal gas constant, which is R, capital R. And so you may see PV equals nRT with a lowercase n and a capital R. Instead, the ratio of the gas constant to Boltzmann constant is exactly equal to the ratio of 1 mole to Avogadro's number, 6.02 times 10 to the 23rd. So that's exactly how you get that. Anyway, there we go. This is the derivation of the ideal gas law. This is how we get it. And it comes from just looking at a particle bouncing around inside a box and then pulling in this idea of how temperature is related to motion. And those two core ideas, along with a little geometry, just lead us to this really fundamental and powerful relationship between these gas properties of pressure, volume, and temperature. This is, I think, really amazing, and it keeps me up until 10 o'clock at night. At least it's worth it. I enjoy this greatly. All right, thank you very much for joining, coming along with me on this journey, and hopefully this is enlightening for you. Ciao.